Welcome. The topic we'll be discussing in this session is deadlock avoidance. The last class we have discussed deadlock prevention technique. So there are two ways to ensure that deadlock will never occur. One is deadlock prevention technique and the other one is deadlock avoidance technique. So deadlock prevention technique basically tries to make sure that at least one of the necessary condition of the deadlock not happens. In deadlock avoidance technique, what we do in the sense, the system, that is the operating system, may need some additional information about how the resources will be requested by the process. Okay, so basically the operating system needs more information from the process about the resource request pattern. Okay, so let us try to understand this with an example. Assume that the system contains only one tape drive and one printer. Okay, the system has one tape drive. I'm calling it as TD. There is one tape drive and one printer. Okay, printer, let me call it as PR. Okay, so there is one tape drive and one printer. And let us assume there are two processes. One is the process P, the other one is the process Q. Okay, say the process P wants this in this order. First, it wants to access the tape drive and then it wants to access the printer without releasing the tape drive. Okay, so this is the request pattern. And Q and process Q, first it want to access the printer. Okay, and then it want to access the tape drive. Okay, so here both the process should inform the operating system. So both the process should inform the operating system. Like so with deadlock avoidance technique, operating system needs more information about the resource request from the process. Okay, so normally the process will not inform the operating system like what are the resources, all the resources it is going to request. No, whenever it needs a resource, it will request and it will get it. Okay, but that may lead to a deadlock. Okay, so to avoid that, the operating system demands that the process should the process should in ahead it should inform the operating system like what are the resources it may need. Okay, if it does not inform, then what will happen, let us understand. Say process P first request for tape drive to the operating system, and let us assume operating system has granted the tape drive to process P. Now process P got the tape drive. Similarly, say meanwhile process Q request for printer, and operating system offered the printer to the process Q. Now the system is having only one printer and one tape drive. Now the tape drive is with process P and printer is with process Q. Now after some times process P will request for the printer, but printer is with Q. Q won't release it. Okay, and after some times maybe Q may want tape drive. So Q will request tape drive, but tape drive is with P and P will not release it until it gets the printer. Okay, but printer is locked in Q. So this becomes a circular wait. This becomes a circular wait. To avoid this type of situations, what the operating system demands, the operating system, what it requires in the sense, it requires additional information about resource request. That is, uh, previously itself, a priori, all the process should inform the operating system like in what order they will be requesting the resource and what are the resource they will be requesting. So in that case, process P will be informing to the operating system that I will be requiring first the tape drive, and then the printer. Okay. Similarly, process Q will say that I will need first the printer and then the tape drive. Okay. Now what happens in the sense, okay, operating system now understands, okay, process P will access tape drive first and then printer, Q will access printer first and then tape drive. Okay. Now let us say that at time t naught, q was uh, q was assigned with printer. Q was allotted the printer. Printer was allotted to the process Q. Okay. This tape drive is not yet allotted, but operating system knows that after some times Q will require tape drive, like that it knows, because it a priori it has collected the information. But at time t naught, let us assume that a printer was assigned already to the process Q. And now say that if process P requests the tape drive, tape drive is not yet allotted to Q, only printer is allotted, and process P is requesting the tape drive. Okay, so even though process P is requesting the tape drive at time t1, and the tape drive is free, but the operating system will not give the tape drive to the process P, because operating system knows that after some times Q will need it, and if it gives to P, then then obviously it will result in a deadlock, because because it will be locked with P, and later P will need printer and Q will need the tape drive. So it will result in a deadlock. So what the operating system will say in the sense, operating system will ask the process P to wait for some times. So operating system will ask the process P to wait. So process P will wait for some times. How long it will wait? It will wait until Q finishes the operation. Okay. So maybe after sometimes at time t2 or time t3, Q may request again for tape drive, and operating system, now already printer is with Q, so operating system will give the tape drive also to Q. Then maybe at time t3 or t4, Q will complete its task, and it will release the printer, and also it will release the tape drive. Okay. So now the process P can be given the tape drive, and after some times it may be given the printer also. So this is how the deadlock is avoided by this technique. That is, a priori operating system needs the information about the various resources and the order in which the resources will be required by each of the process. Okay. So now let us try to understand. Uh, so the so operating system requires that the system has some additional a priori information available. Okay. So there are many algorithms. There are many deadlock avoidance algorithm available. Uh, uh, so basically one of the simple and commonly used algorithm is where each process must where each process must say how many instances of maximum how many instances of each of the resource they will be needing, they will be requiring in advance. Okay. So 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 whatever the deadlock avoidance technique we have discussed so far, that is the overall working principles of deadlock avoidance. But there are many different variations of deadlock avoidance algorithm available. One of the commonly used algorithm, what it demands in the sense, it expects each process uh, to inform the operating system about the the resources maximum number of resources of each type that it may need. Okay. Resource type in the sense, different types of resource we have, like we have a printer, we have tape drive, we have hard disks. Okay, all these are resources, and each resource maximum how many copies this particular process will require, that it should declare to the operating system in advance. Say the process Pi needs a maximum, say there are five types of resource. So resource one, how many instances maximum it may require. Does it require 3 or 4 or what? And resource 2, second resource. Resource 1 may be a printer. Resource 2 may be hard disk. Resource 2, how many instances it may require maximum, upper limit, 5 or 6 or whatever it may be. Similarly, resource 3, like that for all resource, it should in advance say a maximum how many instances of each type of resource they will require. Okay. And so once this information was given to the operating system, the operating system will dynamically examine the resource allocation state. The operating system will dynamically examine the resource allocation state. Okay, that is the operating system will now understand like each process needs maximum how many resources of each type, and it will dynamically examine the resource allocation state to ensure that there is no circular weight. To ensure that there is no circular weight. Okay, so if there is no circular weight, so then uh, uh, if there is no circular weight, uh, then only the operating system will give the requested resource. Otherwise, it will make the process to wait. Okay. So the resource allocation state, it depends on the number of available resources. Number of available resources means number of resources currently available with operating system, which is not allocated to somebody else. Okay. So the resource allocation state depends on the number of available resource, number of allocated resource, and the maximum demands of each process. So based on that, the resource allocation state will be decided. Okay. So if the resource allocation state, if it is not in a, if it does not, if it leads to a circular weight condition, then the operating system will ask few process to wait until some of the resources were released by the other processes. Okay, so this is how the deadlock avoidance algorithm works. Okay. Now let us try to understand a concept called safe state with respect to deadlock avoidance algorithm. Okay, so the resource allocation state, it will try to understand. So here we have discussed that the operating system dynamically examines the resource allocation state to make sure that there is no circular weight. Okay, so if there is no circular weight, if there is no circular weight, then it means that the system is in the safe state. So let us try to understand how the operating system will detect whether the system is in the safe state or not. Okay. So let us try to define safe state. The system is said to be in the safe state if it can allocate resource to each process in some order such a way that there is no deadlock. The system is said to be in safe state if the operating system is able to allocate resources to each process in such a way that there is no deadlock. Okay. So process requires resource and system must identify some order to ensure that there is no deadlock. Okay. So the system is said to be in safe state if there exists at least one safe sequence. The system is said to be in safe state if there exists at least one safe sequence such that P1, P2, Pn. So where P1, P2, all these are processes. Okay. Where where for every process Pi, where for every process Pi, whatever the resource it is going to request, whatever the resource it is it is going to request, it is going to request in the future can be satisfied by the available resource, whatever the resources that will be executed by the process pi, by all the process pi. Okay, by each process, whatever the resources that will be requested by each process pi in the future will be satisfied by the available resources, that is the resources that were currently not allocated to any process, by the available resources sorry, by the available resources and the by the available resources and the resources that were allocated to the process Pj, and the resources that were allocated to the process Pj, in such a way that j less than I, such a way that j less than I. So what does it mean? What does it mean j less than I? See, so let me define again. So the system is said to be in safe state if there exists at least one safe sequence like P1, P2, P3 up to Pn, where each of the Pi is a process. Okay. So the system is said to be a safe state if there exists at least one safe sequence such that for every process Pi, for every process Pi, whatever the resources that it is going to request in the future can be satisfied by the available free resources plus the resources that is currently being held by the process Pj, where Pj is less than I. So what is less than I means? Okay. So let me say that. So here if you see P2 is less than P1. So less than means the process P1 comes before P2. So that is what less than. Okay. Similarly, P2 comes before P3. P3 comes before P4. Like that. Pn minus 1 comes before Pn. So if you take P2, if you consider Pi as P2, okay, that is if you consider I as 2, then then that for every pi it should be satisfied, okay, right? Then the number of resources that pi is going to request in the future should be satisfied by the available resources, and by the resources that were held by pj, where j is less than I. So it means that were held by p1. Okay. So this is the case if I is 2. Okay. If I is 3, if I is 3, then it means that whatever the resources that P3 is going to request will be satisfied by the available resources plus the resources that were held by P2, that were held by P2. Okay, so this is the meaning, right? But if you take P1, that is the first process. If you take P1, for P1, there is no previous process. Okay, there is no process which is less than P1. Okay, so in this case, if you take if I is equal to 1, if I is equal to 1, then P1 or Pi, whatever it may be, if I is 1, then whatever the resources that were going to be requested by pi in the future should be satisfied only by the available resources, because there is no pj, such a way that j is less than I. Okay. So this is what a safe sequence is, right? So uh, let us try to understand uh, this with an example. Okay. So this is so each pi, the resource pi that it can still request should be satisfied by the currently available resource plus the resource held by pj, where j is less than I. Okay. So let us try to understand this with an example. Consider that we have three processes. Let us assume there are three processes given by p naught, p1 and p2. So let us assume we have three processes P0, P1 and P2, and let us so there are so so the deadlock avoidance algorithm, each process should already a priori it should inform the maximum instance of each of the resources that it may require. Okay, so this is maximum requirement, maximum need. Okay, so process P0 may require 10 instances of process P0 may require 10 instances of tape drives. Okay, and process P1 may require maximum 4 instances of tape drives, and process P2 may require maximum 9 instances of tape drives. Okay, and let us assume the system contains 12 instances of tape drives. The computer, the currently whatever the system we are using, let us assume that has 12 tape drives. So it has 12 tape drives. Process P0 can maximum request for 10 tape drives, and process P1 maximum can request for 4 tape drives, and process P2 can maximum request for 9 tape drives. Okay, now, and say that current, so this is the maximum need. Now currently, how many are allotted? Let us understand that. Now currently how many are allotted for each of the process? So currently 5 tape drives were allotted to P0. It may need another 5. And currently 2 are allotted to P1. It means it needs another 2. And currently 2 are allotted to P2. It means it may need another 7 over a period of time. And the system contains 12 tape drives, and already 5 plus 2 7, 7 plus 2 9, 9 were allocated. So the remaining available tape drives, what is the available tape drives? Available tape drives are 3. So this is the available. Okay, now our job is to find a safe sequence. Our job is to find a safe sequence such a way that this all the process can get all the resources without any deadlock. Okay, so one of the safe sequence is here the safe one of the safe sequence is p1 comma p0 comma p2. This is a safe sequence. In this example, p1 p0 and p2 is a safe sequence. Okay, let us understand why it is a safe sequence. So it means this is the sequence. You should follow this sequence. First p1 should execute. First P1's requirement should be satisfied. Okay, so P1 already got 2 tape drives, and how many it needs? 2 more it needs. So give that if it requests, let us assume. So even though if so here P1 is first in the sense, what you mean, what in the sense, uh, say P1 may not request the tape drive currently. P0 may be requesting. P0 may be requesting, but the operating system should not give if P0 request, because that may not be a safe sequence, because we identified that this is the safe sequence. This sequence will ensure that the system will not enter into a deadlock. So now if operating system if the process p0 asks give me one more tape drive, operating system should not give. It should ask p0 to wait. Similarly, if p2 asks give me 2 more tape drives, operating system should not give even though it has. It should ask it to wait, because that is not the safe sequence. Okay, so only if p1 asks it should give. Okay, so let us assume that p1 asks another 2 tape drives. It needs maximum 2. Already it got 2. So another 2 is allotted to p1. So all its requirements are satisfied. Okay, then what will happen? It may execute for some more time. Say it executes for another x amount of time. After executing for, so once these 2 tape drives were given to p1, then the number of available resources is 1. Number of available resources is 1. Okay, but p1 will execute maximum for say x time units, and then p1 its task is completed. Once its task is completed, it will release these 4 tape drives also. So now the available resources are 1 plus 4 5. 1 plus 4 5. Okay, now you have 5 resources. So first you have given p1 to execute. Now p1 has finished execution. Next, who is in the sequence? P0 is in the sequence. So now we have remaining 5 tape drives, and P0 needs exactly 5 tape drives because already it got 5. Okay. So now even if P2 asks, you should not give, the operating system should not give. Now allocate these 5 tape drives to P0, and P0 may use this, may say some amount of time, another Y amount of time it will use. After that, so once you allocate all the 5 to P0, then the available resource is 0. Okay. Then so P0 will use all these 10 tape drives, and finally after Y amount of time it will complete, and then it will release all the 10 tape drives. Now the available resource is 10. Available tape drives are 10. Now at last you give to P2. Okay. Now P2, the remaining 7 tape drives give to P2. So if you give 7, 3 will be remaining. Okay. So 2 plus 2 plus 7 9. Now P2 got all the tape drives and it may execute say another z amount of time, and after that it will complete. So once it completes, it will also release all the tape drives. So the available resource will become 12. So this is a safe sequence here. So this is a safe sequence here. Okay. But assume that, but assume that instead of following this safe sequence, instead of following this safe sequence, let us assume something else. Okay. What is that in the sense? Yeah. Okay. So this is a safe sequence here. But but assume this situation. Consider this situation. So this is the current situation. So the safe sequence is P1, P0, P2. Okay. Uh, but assume that at time T1, at time T1, P2 is requesting one more tape drive. P2 is requesting for one more tape drive. Okay. So say P2 is requesting for one more tape drive. Okay. And assume that and assume that the operating system has given that tape drive to P2. So P2 got 3 tape drives. Okay, P2 got 3 tape drives. And what will be the available tape drives now? So initially the available tape drives were 3. Okay, and out of that 3, one is given to P2 now. So the available tape drives were, now the available tape drives is only 2. Now the available tape drive is only 2. Okay, now the available tape drive is only 2, right? Say this 2, say later P1 asks this 2, okay, and you assign this 2 to P1, okay. Now the available tape drive is 0. Now the available tape drive is 0. Now after some amount of time P1 will complete. P1 will complete and it will give all the 4 tape drives. It will give all the 4 tape drives, but the problem is it gives all the 4 tape drives, but uh, but P not needs how many more tape drives? 5 more tape drives, but we don't have 5 more tape drives. And P2 needs how many tape drives? It needs totally 9. Already it got 3, so it needs 6 more tape drives, and we don't have that. Okay, because available tape drive is 4. So this 4 tape drive, it cannot satisfy the requirement of P naught, and also it cannot satisfy the requirement of P2. So the system will enter into a deadlock or an unsafe state. Okay. So this is how we define the safe state. So a state is said to be safe if there exists a sequence such a way that P1, P2, Pn, and for each Pi, the request that will be made in the future can be satisfied with the current available resources plus the resource held by Pj where j is less than I. Okay. So this is how safe sequence is defined. I think you got the point, right? So the takeaway point is, if the system is in the safe state, then there is no deadlock. If the system is in that safe state, then you can ensure that there is no deadlock. On the contrary, if the system is in the unsafe state, then there is a possibility of deadlock. If the system is in unsafe state, then you cannot say always there is a deadlock, but there is a possibility of deadlock. Okay. So the deadlock avoidance algorithm, what it ensures in the sense, it ensures that the system will never enter into unsafe state. Because if it enters unsafe state, then there is a possibility of deadlock. So this diagram clarifies the thing. If the system is in the safe state, then there is no deadlock. Okay. In unsafe state, every unsafe state is not a deadlock state. Say for example, these are not deadlock states. Okay, but deadlock is an unsafe state. Okay, every unsafe state is not deadlock, but deadlock is an unsafe state. Okay, so that's the point. So So there are the avoidance algorithms are basically implemented in two ways, either by using resource allocation graph or by using Banker's algorithm. If if each of the resource there is only one instance is available, then resource allocation graph is used. If multiple instances of each resource is available, then Banker's algorithm is used. Okay. So let us try to understand the first algorithm now using resource allocation graph. See, resource allocation graph, we have already discussed resource allocation graph. But in this context, in deadlock avoidance, uh, we are introducing a new edge here, and this edge is called as claim edge. And this edge is called as claim edge. That is, uh, the process pi may claim a edge Ri. It is in the future it may request it may require an edge Ri. So edge pi tends to Ri. It indicates that the process pi may request the resource Rj in the future. Okay, and this is represented by a dashed line, and the claim edge is represented by a dashed line. So basically, it means that the process pi may require the resource in the future. Basically, claim edge means that the process pi may require the resource Rj in the future, and the claim edge is represented through dashed line. So here we introduce a new edge which is called as claim edge. All the other things are same. Vertex, two types of vertex. One is process, the other one is resource, and the claim edge will be converted to a request edge when the process requests the resource. Okay, request edge we know pi is requesting the resource Rj, and the request edge will be converted to assignment edge if the resource is allocated to the process. Okay, so assignment edge, it comes from resource to the process. Similarly, when a resource is released by a process, if a resource is released by a process, again the assignment edge will be converted to claim edge, because again in the future it may recur. Okay. So with this basic understanding, let us try to uh, move to resource allocation graph, and let us see using resource allocation graph how deadlock can be avoided. So let us see this graph. So this graph, what it represents, it represents that there are two process P1 and P2, and there are two resources R1 and R2. We have only one instance of R1 and one instance of R2, because there is no inside, there are no squares. Okay, and what this arrow represents, the resource R1 is assigned to P1. So this is an assignment edge. This is assignment edge. The resource R1 is assigned to the process P1. Okay, and P1 may claim R2 in the future, because it's a dashed line. So P1 may claim the resource R2 in the future. And so this line, what it represents, P2 is requesting the resource R1. P2 is requesting the resource R1, but R1 is already assigned to P1. And P2 may claim for R2 in the future. That is, P1 also may claim and P2 also may claim for R2 in the future. That's the point. And R1 is currently allocated to P1, and P2 is waiting for R1. Okay, it is requesting R1. Now let us say that, now let us consider P2 is requesting the resource R2. Let us say, so here already we discussed that P2 is what we have discussed. P2 may claim the resource R2 in the future. Okay, say assume that now P2 is requesting the resource R2. If P2 is requesting the resource R2, then actually R2 is free. Actually R2 is free, because R2 is not allocated to anybody. P1, this is a claim edge. P1 also may claim in the future. So R2 is free, but operating system should not allocate R2 to P2. but operating system should not allocate R2 to P2. Why? If it allocates, what will happen? If so, this is an assumption. It's not real allocation. It's an assumption. If R2 is allocated to P2, then what will happen in the sense? Then there will be a cycle in the graph. There will be a cycle in the graph. The cycle will be from R1 to P1, P1 to R2, R2 to P2, and P2 to R1. Okay. So if there is a cycle, if there is a cycle in the resource allocation graph, then that is not a safe state. If there is a cycle in the resource allocation graph, then that is not a safe state. Okay, so this is how, using a resource allocation graph, we can avoid deadlock. So whenever whenever a process requests a resource, you should not the operating system should not immediately allocate the resource, but the operating system should assume the resource is allocated, and then it should check in the resource allocation graph, assuming the resource is allocated, is there any cycle? If there is if there is a cycle, then it means that the system will enter into a safe state, and so that request should not be accepted. Okay, so this is the concept. Suppose the process PI requests a resource RJ, the request can be granted only only after converting the request edge to the assignment edge does not form a cycle. Okay, if any process PI requests a resource RJ, the request should be granted only if the request edge after converting to an assignment edge, if it does not create a cycle in the resource allocation graph. If a cycle is created, then the request should not be granted. That's it about resource allocation graph. So we have discussed about deadlock avoidance technique. So basically in deadlock avoidance technique, the operating system needs a priori information about the process, like what are the resources it will require in the future. And we have discussed the safe state, how to define, how to identify whether the system is in the safe state or not. Okay, in the safe state, there is no deadlock. So the deadlock avoidance algorithm ensures that the system will never enter into an unsafe state. And also we have discussed using resource allocation algorithm, resource allocation graph algorithm, how deadlock can be avoided. Okay. So let us stop here. Thank you.